Thanks, Derek.
Dan, your research specialty is something called uncertain data. What is that?
So can you hear me? So uncertain data is data that has something missing, that is not precise enough to feed into an application. It might be as simple as an attribute is null. You don't know what the value is. Quite often, you have multiple options for that attribute. There are multiple possible values, and you don't know which one is the right one. Sometimes these values are actually conflicting. They come from conflicting sources. They can't be all true, and sometimes you need to account for the fact that you trust some sources more than the others. So uncertain data is actually quite prevalent today. And one of the instances of uncertain data is what people call unstructured data. And this is data that does not have a schema. It's not labeled. We don't know the context. It's unstructured. It's not suitable for traditional applications. This can be data found in text. There is a lot of interesting research on crawling the web and extracting structured data from web pages. There is so much information out there. If we could just take it and put it in a database, that would be a fantastic thing to do. Sometimes the data is in images. Some people actually, they are quite advanced. They extract information from figures in papers. They look at the graphs, and they can extract from that PDF file for structured information that can be stored in a database and later processed. Quite amazing. So this is the kind of data that excites me. There is so much data out there that is uncertain. And part of my research is how can we actually make use of it.
Awesome. So you mentioned databases, and I think one of the challenges for people who work with uncertain data is databases, at least the classic databases that most of us work with on a daily basis. They store facts, right? They store certainty. And so when you're working with uncertain data, you need these new types of data systems. So sort of describe the relationship between uncertain data and these probabilistic data systems in the context of, it's different from what we're used to.
Right. So we need to deal somehow with this vast amount of uncertain data. And it's not possible to repair it. It's not possible to automatically figure out how to fix it. So the right model for such data that came out of academia is to use probabilities. So whenever you don't know a value of an attribute, you just record all the possible variants, and each of them with a probability that you associate to this. So I came up with an example that I think is fun. Suppose you find on a website the string Michael Jordan. Now, everyone in this room knows who Michael Jordan is. The problem is that there are actually two famous Michael Jordans. One is a basketball player, but the other one is one of the top leading experts in machine learning. He's a professor at Berkeley. And if you tell me the name Michael Jordan, I immediately think of the Michael Jordan at Berkeley, while you might think about the Michael Jordan, the basketball player. So what should the system do? Well, simply record both instances. It might be this Michael Jordan or that Michael Jordan. Use information from the context, from the website where you collected it, and maybe assign a probability to this option or to that option. Keep all this information around and use probability theory to model the data that you have. So this is how we use probabilities in order to capture and model and process uncertain data. We just store all the possibilities together with their probabilities. Hopefully also capture the correlations between these possibilities. And then we have a challenge of actually managing such data.
Right, so I have, what I take from that is I have a really fancy database where instead of just storing the fact of Michael Jordan's identity, I have multiple facts. But then what can I do with that, right? Like what can I do now that I have this, fancy probabilistic system with these different, linkages with the probabilities assigned that I maybe can't do with a classic system?
So once you have probabilities, you need to figure out what to do with them. And there are essentially we can think of three ways to manage probabilities. And the simplest one, which people do today, is to use a threshold. You set a threshold like 0.7, and all the facts whose probability is above 0.7, you take them as given. They are true. And all the facts that are below 0.7, you just throw them away. This method is simple, it's appealing, but it's very limited. It's limited because later you want to change your mind. You might want to lower the threshold, or you might want to increase the threshold, depending on your application. It's very difficult to go back and modify the threshold because all your processing downstream now depends on the decision you made with this threshold. The second alternative is what machine learning people call the MAP, or MAP, the most a priori probability. So you look at your entire data, and for each fact, you choose the alternative that is the most likely, that is the most probable. And you take all the correlations into account. It's complicated, but it's well understood how you compute this. And the result is, again, is a clean data set that is structured, that is certain, but it's only one of the many alternatives. So for example, if you have a customer, John Doe, and you don't know in which city this customer resides, you have 5 alternatives. For each of them, you have a probability. The MAP will just choose the city with the highest probability. And that is what you retain. And the other 4 alternatives, you throw them away. This is good for high precision. You get the best precision you can from your uncertain data, but it is not good for recall. You're losing a lot of information. You're throwing away lots of information. The third alternative, and this is what really excites me, because this is exactly what Derek proposed when he came to my office in that famous day. He said, let's get rid of the threshold and this MAP. Let's just keep all the probabilities. And I thought, yeah, this is what we do in probabilistic databases. So the idea is very simple. You just keep all the options, all the variants together with the probabilities, and then you have to worry about how to modify all your applications or your database management systems to handle these probabilities. But at least you have them there. At least you can answer this simple question, how many customers do I have? Because you can compute the expected value of the number of items that are your customers.
Got it. So, and you alluded to this, like once, sort of conceptually, these are the ways to think about and store and manage probability. But, in a classic data system, if I want to answer the question, how many customers, I just say, select count star from customers. It's very simple. So how do I actually use a probabilistic data system to work with this data?
Right. So using it, that's challenging. This is what drives drives me and my research and my students. And this is what Amperity is also facing. How do we actually manage and use probabilistic data that captures uncertainties? So traditional database systems, they have addressed 2 aspects of data management. One is transaction processing. That has to deal with very precise data. That is not the topic of probabilistic data. And the second function that they serve is that of online analytical processing or decision support. This is when we ask questions like, how many customers do I have in my database? This function needs to be enhanced with the ability to process probabilistic data. Sometimes it can be very simple, but it gets complicated pretty quickly, especially if you want to ask very complicated queries. But the purpose of a probabilistic database is to act like a standard relational database. It manages records, but now the records, they are annotated with a probability because they have multiple alternatives, either in their values or in the record itself. And the database system needs to manage all these alternatives.
So we're talking about these probabilistic data systems, and and there's a whole lot of sort of technical challenge just in building a system of this type. Layered on that, there's this notion of learning the probabilities themselves. So I guess explain the relationship between machine learning and probabilistic data systems.
So machine learning. So I noticed that you listed me as an expert in machine learning, and I like to make a correction. I'm actually doing research in data management. I'm not a machine learning expert, but there are some great experts at Amperity. Probabilistic database systems, they are actually both users and consumers of machine learning. One thing that people are often not aware is that when you do data analytics, when you do machine learning, most of the time of the data analyst is not spent running the machine learning algorithm, but is spent in collecting the data, cleaning the data, integrating the data. Then you run your machine learning algorithm, you don't like the results, you go back to collecting and cleaning and processing the data. So this is a place where probabilistic database systems have a role. But there is also the other role, that of consumer of outputs of machine learning. So if you think, for example, about logistic regression, which is a standard machine learning algorithm, it looks at a record, and it needs to classify it into type A or type B. Produces a probability based on the features of that record. It says with this probability is type A or type B. Amperity deploys logistic regression. It looks at a pair of records and decides with what probability are these, do they represent the same record, or no, they are different records. Also, a classic example, a very popular example in processing unstructured data is that of text segmentation, or more generally, information extraction from text. When you try to map raw text into structured data, you end up with a probability distribution on the way to structure this data. One such technique is called conditional random fields, and that results in a probability distribution on the way to structure the input data. So now imagine that you have this machine learning algorithm that runs over a large collection of inputs, and for each of them produces a probability or an entire probability distribution on how to structure or how to interpret this data. This would be the input to the probabilistic database system. And later now, the database system needs to be able to manage and process this probabilistic data.
So probabilistic data systems are considered pretty cutting edge. Probability as a concept is not new. I think I learned about that in grade school. So I guess why is this cutting edge? And I guess why now?
So it's true. So probability theory seems simple, and it is simple. The problem is when you face correlations, and you need to do probabilistic inference in the presence of correlations, and this happens in the case of large data sets. When you process it, even if you don't have native correlations, when you process the data, you introduce correlations. The classical, the simple way to model probabilistic databases is simply to think about each record as being independent. You have the value of an attribute, and this record is independent of the value of that attribute in a different record. But in practice, often these probabilities, they're actually dependent. So for example, one example I like a lot is at Google, they had this research project called the Knowledge Vault. And the Knowledge Vault consisted of, it's a large knowledge base that is probabilistic, that was constructed automatically by crawling and doing information extraction over pages on the web. Of course, they have access to all the pages on the web. And they did not develop their own, in this Knowledge Vault project, they did not develop their own information extraction system, but instead they used like a dozen or so extractors that already existed in Google. And different extractors, they had competencies for different kind of extractions, and then they used all sorts of integration techniques to produce this large knowledge vault, which was essentially a probabilistic knowledge base. Now, different extractors, they have different degrees of accuracy. So if an extractor is not that good, it means that all the facts that it has extracted, they have a low confidence, but this confidence is correlated. If the extractor is good, then all of them are actually better. So the fact that the same extractor contributes to a large number of tuples introduces very complex correlations between these probabilistic events. This is what makes processing on such databases challenging. The fact that we are dealing both with large amounts of data and also with a complex probabilistic space. And this is what I find exciting, because we need to combine both techniques from query processing in the relational databases, which has its foundations in mathematical logic and relational algebra, with probabilistic inference, which has foundations in probability theory, and also in graphical models and machine learning.
By the way, if you've ever searched for lemonade on Google and wondered to yourself, how did it know I was looking for the Beyonce album? That was the answer to that question. So you're dealing with cutting-edge research here, and obviously there's a lot of hard problems in this space. I guess as you look out ahead, what are sort of exciting new things that we might be on the verge of solving that might lead us to even more interesting insights?
So what excites me is understanding the complexity of how we process queries on such large probabilistic databases. So some queries are actually deceivingly simple to process. If you just need to join two tables, you just multiply their probabilities. But it quickly gets complicated. If you have a more complicated way to process the data, you need to join them, to duplicate elimination, then the queries become provably hard. And one of my research was to study this boundary between the easy queries and the hard queries. We're still at the infancy of understanding how to process very large probabilistic databases. But it's kind of unavoidable. Uncertain data is now predominant, is abundant, and it's going to be everybody in this room is facing large amounts of uncertain data. And companies that are at the forefront of using data-driven decisions, they are aware that these uncertain data are a very valuable source for their business, and they look for technologies. Or they look at least for ways to store and record this uncertain and probabilistic data. But still, we don't have the techniques yet to the general purpose techniques to handle such data. I have one example. I don't know if you follow this. Apple bought recently a company called Deep Dive, which is a system that essentially allows you to quickly deploy a large information extraction system that crawls unstructured data and produces a structured probabilistic knowledge base. So in Deep Dive, you need to hire some very smart engineers to set it up. But once it is set up, you can actually crawl text, you can crawl images, and then the probabilistic inference itself, it computes an MAP, by the way. So it does not store probabilistic probabilities natively. But even this MAP is hard to compute. And the report running an MCMC and Monte Carlo Markov chain algorithm for about 10 hours or so on a very large server. So this is what you need to run, and then you look at the results. You don't like them and go back and repeat. So this is where the technology is today. And I expect in the future, companies like Amperity will identify interesting applications that require new ways to process this probabilistic data. This new way requires innovation and probably more general purpose tools that are more efficient than what Deep Dive produced. So by the way, two of the co-founders of Deep Dive were actually my students, Chris Ray, who's a professor at Stanford, and Mike Affarella, who's a professor at Michigan. So they did very well, and they got a bug for thinking about probabilistic data when they were PhD students at the University of Washington. So Chris Ray did an amazing job on probabilistic databases.
And one of those is a MacArthur Fellow, and the other one founded Hadoop. So
yeah.
pretty good.
It's true. Chris Ray is a MacArthur Fellow, and Mike Affarella founded Hadoop.
Awesome. Well, Dan, it's been tremendously fun to be on this journey. You know, it started off with us realizing it was going to be very difficult, but it's possible. It's become more possible with each stage that we've gone through, and it's been fun being on the journey. So thanks so much for being a part of it.
Thanks, Derek.